What do we mean by standard? It means to bring into conformity or done in a consistent way. To measure the electrical potential of a cell, one employs the standard hydrogen electrode, to which all other half cells can be compared. Let's look at that cell, sometimes referred to as the she. Hydrogen gas pumped at 100 kPa and 298 Kelvin is pumped over a platinum electrode that's immersed in an acid solution that has a concentration of hydrogen ions of 1 mole per decimeter cubed. We connect it up to our test cell. Here I have a set of values that are available in your IB data booklet, and I'm going to look at the particular location of the hydrogen and the copper here. So we'll look at the bottom two. A positive cell indicates that the oxidized species has a greater tendency to gain the electrons than the hydrogen. So in this case, copper wants to gain the electron, and it would move over in this fashion. Since the copper is gaining electrons, that would constitute the cathode, and therefore the hydrogen would be the anode. Let's replace the copper now with zinc. In this particular case, we have a negative voltage. That indicates in our situation that the H+ ions have a greater desire to gain electrons than the zinc. Now we have a much larger table than these three in your IB data booklet, so we'll take a look at them. I would like to determine the standard electric potential for this cell. This is the standard cell notation we use to communicate what's in a cell. So iron with an iron solution, salt bridge, copper, and a copper solution. And here is the somewhat expanded table of values from your IB data booklet. Let's begin by identifying the two electrodes that are present on the table. I noticed that the copper ion is down below the iron ion. That tells me that copper ions have a greater potential to gain electrons at plus 0.34 volts versus the iron ions, which are at negative 0.45. So I know then that the copper side is going to gain the electrons, and they'll move in this fashion. Since it gains electrons, that constitutes my cathode. So that reaction is going to occur as it's written here in the data table. The other side, though, is losing electrons. That means I need to reverse the reaction at the anode. So those would be my two half-cell reactions, and overall, adding the two together, ensuring the electrons lost and gained are the same, I would arrive at the following. But what's the voltage of this particular cell? Well, we need to look at the difference that exists between these two numbers. So we use this formula. The electron potential of a cell is the E at the cathode minus the E at the anode. Substituting in the values from our table, we arrive at positive 0.79 volts. I want to look at another way that we can use this table. It can be used to judge whether reactions are not spontaneous or spontaneous. Is the reaction between copper and nickel spontaneous? A spontaneous reaction will occur when the cell potential is positive. So copper and nickel. Those are the two reactants I want, so I'm going to identify those reactions in the table. The first thing I'm going to do now is notice that the nickel reaction I can copy down as is, because nickel is both the reactant in my target equation and the one provided in our IB data booklet. However, the copper is on the wrong side. I need to reverse that reaction and as a result, reverse its voltage. Adding those two together, I get negative 0.70 volts. This would be a not spontaneous situation. Conversely, if I take a look at tin and a lead-2 solution, I'll identify them again on the table. I can see that the lead is in the correct position. Lead ions are both reactants in the data table and in my target equation, so I can leave that equation as is. The tin, however, the tin solid, I need to get that over to the other side. I need to reverse that reaction, hence I'll reverse its sign by using the negative of it. I can now add together these two values and arrive at the voltage of my cell. Since it's a positive value, this would be a spontaneous reaction. So I hope you found that useful. Questions are always welcome.